All right, so welcome to the first episode for Scientifically Simple. This is just going to be an introduction of what we hope to provide to you, our audience. So, a couple of things to highlight. One, this is going to kind of review our episode structure. So, you're going to see an introduction to kind of high level review what we hope to cover, go into the meat of the material, so whatever the main subject matter is, summary what is discussed, and then we're going to talk about kind of what is relevant in engineering today, such as, I don't know, a new invention, technology, something safety related, something like that. And you're probably wondering yourself, what makes you different than all the other videos out there? Well, our ultimate goal is to try and create material that can make you, as the listener, viewer, whatever, a better engineer, a better scientifically driven individual. So a little bit back about us. My name is Brandon. My colleague is Mohammed. We've known each other for about 7 years now. 6 years? 6 years going on 7 years. I have a bachelor's in chemical engineering, pursuing a professional engineering license, and then Mohammed actually has a master's in chemical engineering, professional engineering license, working full-time, and was bored, and now he's getting his PhD. So that's a lot, but I'm going to pass the reins over to my colleague.
Thanks so much, Brandon. As majority
And for
of
what it's
people
worth,
nowadays,
the smartest guy I've ever met. So just, I don't want to set the bar too high. Absolutely brightest mind I ever met. Okay, I'm done.
I appreciate that. Thank you, Brandon. And most of people would be knowing me nowadays as Mo Short, especially that came along during the crazy days when triathlons and marathons times for myself started to kick in back in 2019, just almost like 1 month after the pandemic. But anyway, thank you for listening to us, and we are looking forward to be presenting for future engineers and undergrads who are interested in practical engineering, where we can connect everything between what we see in our textbooks in different classes with what we are observing, whether we get to be in a co-op opportunity or internship opportunity, or even like you are senior, already graduated, about to be kicking into the amazing life of having to live through an engineering career. That's where we're trying to bridge between academia and the current established industrial standards.
Right.
And
Well, I was just going to say, so kind of what made this appealing to me, right? So when Mohammed and I first met, I considered myself an accomplished engineer. And then I started working with him, and I realized that I really didn't know what I was doing. And it's not that I wasn't intelligent. There is a massive gap between what you learn in school and how you apply it in industry. And I did not recognize that until I started working with Mohammed. So a lot of our goals here are to help connect those dots.
Absolutely, Brandon. So that's literally, it was based off of a personal experience myself. Like, I got, given all these years of experience since I graduated, I got to be seeing from the beginning there is this gap between industry and academia. You can, of course, basic foundation wise, you should be knowing, a compressor would eventually have to be following laws of thermodynamics. But there is this weird blurry fog when you actually first time go to a chemical plant and you look at the compressor and you just you feel like there is some type of a struggle, or you look at the chemical reactor if you are a chemical engineer, and you're trying to be how I can use what I have learned back in kinetics class or what I have used in thermodynamics class to actually understand or basically break apart or into elementary pieces this compressor where I can understand
it. Yeah.
You get to, for example, to look in a thermodynamic class versus fluid mechanics class and chemical kinetics class, or engineering structure, or if you're a civil engineer, the biggest thing that you are going to notice right away, how insanely integrated all the subjects in industrial life. and how like you need to be connecting all these things in order to basically save yourself some time and effort in order to understand the majority, the 80-20% rule, the majority of what's going on in the chemical plant or the industrial plant that you're going to be working in, or you're going to be ending up in working for an engineering company that will be engineering a plant. So this is another part of of gap that happened between academia and industry, where like everything that has been taught in classes is always like almost like a oasis or an island, isolated island.
Right.
Like, hey,
Yeah.
we have thermodynamics this semester, we have this fluid mechanics next semester, then we move on having like calculus 1, 2, 3, and 4. But like one of the things that you are going to notice once you jump into the career itself, you are going to need to actually collect all these amazing classes that has been taken in college, and trying to integrate them and know where each one of them role is. Like I need to understand like where's thermodynamics fits in this, where's transport phenomena fits in this. Is it like a fluid mechanics limited issue, or is it like a chemical reaction kinetics limited issue? Is it like a matter of flux limitations, like a high viscosity heat transfer through a high viscous material, or is it like a problem into the overall heat transfer coefficient itself, or is it like a thermodynamic limitations where you're actually almost at thermodynamic equilibrium, so that there is no flux anyway, so that you are literally sitting in a physical equilibrium there. So these are one of the just core examples of why if you look at the trends in 60s and 70s and all till now, you'd find that this gap has been growing bigger and bigger between academia and in the industry. And I don't think like it's really like impossible to connect them. It just like on an average, just that gap has been growing, but like it's way easier than people think in terms of like if we can bring them back together or harn or kind of integrate them, where you can find this integrated beneficial cycle of industry providing R&D equipment, R&D funds, ideations, and the academia, on the other hand, pushing the frontiers of science in order to develop new methods and new applications where makes the process way more efficient. So that's pretty much like the goal of this channel, and that will be like including so many as there's gonna be like three categories, as Brandon highlighted. There's gonna be like the category where we're talking about fundamental things, basically the basic foundations of thermodynamics, first law, second law, etc. And then you have the transport phenomena that will come later on. Then you have this part where like how if you look at the industrial plant, that industrial plant can be broken down into so many process units, small pieces. Like
Right.
there is a
Yeah.
valve, there's a relief valve, there is a heat exchanger, and all these things, and we basically laser focus, put it under microscope, how I can rate that, how I can design that piece. And then there is the third category where it's going to be like kind of fun, where we can look at every single technology out there chemical wise, and basically look at like key performance indicators. What actually makes a specific technology or a technology licensor claim that I am doing great and you should be
Oh, that
buying my
sounds fun.
license?
Yeah. Yeah.
So there's gonna be lots of this is probably the fun category, but the sweet part about this fun category is it's like built like a pyramid. You have to know your foundations, then you have to know how from those foundations design every certain elementary piece of equipment that will be utilized later on to build that big industrial plant. And then eventually we go into like the bigger pieces, was like you're moving from a cell into an organ, for example, or tissue, and you'll be like knowing how that whole plant works like.
No,
So,
you're good.
like, I mean, one of the things about the thermodynamics beauty there is that since I started, working out and focusing on, the other part where I'm training for a marathon or a triathlon or something, you just like because of your your nerd side is trying to be thinking stuff like, okay, how whatever performance I'm doing in a marathon, for example, and it's a cardiovascular exercise or aerobic exercise as you claim, and then you find out like later on, that there isn't much. They resemble, so they are super close in a biological
Right.
system to a
Yeah.
Rankine cycle. So you have in a Rankine cycle, for example, you have some type of fuel, natural gas, coal, anything, and you are using oxygen, which comes from air, and you are basically releasing all this potential energy inside the fuel, turning into flue gases. That energy turns water into steam. That steam go into a turbine that either drive a compressor or a generator to make electricity. And then that water that steam get condensed, and the cycle goes on. That's how you end up having a continuous steady state process. Now you look at the biological equivalent of this, which is pretty much
Yeah.
almost the same. You have like again air that you're breathing through your lungs, but like the difference in this case, you have a circulatory system that pretty much selectively takes oxygen, which is your hemoglobin in your blood, and that basically gets dissolved in your blood, meets all the whether it's fatty acids or carbohydrates, and that's your fuel. That's the cell fuel, and basically combust that. You have the same end products, and in doing so, it turns something called ADP into ATP. So ADP is basically the water liquid form of this cycle. ATP is the steam vapor form of the cycle, where once the ATP is provided, the muscle can be able to do work, which is pretty much is the contraction. That's what the muscle work is. And again, like every other heat cycle that we have learned in thermodynamics, you can't turn 100% of your energy or heat energy into mechanical energy. That's how it always works. There's going to be some type of heat released to the environment. That's also how it works in biological aerobic system as well. That's what literally makes us sweat so hard when we run in a hot day, for example, because not all the energy that we are burning actually makes us just like run. Like
Yeah. So I
almost
gotta be
makes.
totally honest with you. I had never thought about it till you said that. It makes so much more sense.
Yeah.
Like when you
Yeah,
point it out like
absolutely.
that your body's actually rejecting
Yeah.
that heat and it's actually
Uh,
raising the temperature of your system.
uh,
And that's why you feel hot and that's why you feel fatigued.
Absolutely.
And I mean,
Hmm.
I've just never thought about it like that. That's really cool.
And I mean, like it's absolutely stunning. I mean, like it's almost like you're talking about 60% of the energy that you are utilizing end up being turned into heat. Only 40% end up being providing the useful contraction work
Yeah,
that you
that's
actually do,
nuts.
which
That's
is
nuts.
crazy. It's like,
Yeah.
because like that heat it is like double whammy. It's gonna end up like making you sweat. It's gonna make your like blood thicker, and your heart has to be like working harder. And on the other side, it's like energy that you cannot like right away replenish it. It's like it's gonna take some time to actually put them back to be as glycogen in the muscle. So yeah, there's a lot of articles out there and papers that are trying to how to upgrade the performance of elite athletes, etc. And it's because, but like on the fundamental level, that's how it looks like, and that's what's always required. Like before going to the kind of low Nobel Prize kind of like ideations, like I want to be like I want to break the heart of the black hole. I want to describe how the black hole functions at the center, but at the same time, I don't understand what's Newton's second law. That's the problem. So we always know, and we always need to be knowing our fundamentals before moving to that advanced level. It's always going to be a pyramid approach in that sense.
So thermodynamics tells you where you're going. It doesn't tell you how do you get there. And I gotta be totally honest with you. I absolutely cannot stand transport phenomena. It is, to me, it is one of the most difficult subjects out there because it's not, to me, it's harder to grasp than thermo. Thermo is very easy to get a grip on.
Mm-hmm.
Transport feels like it's like trying to grab water with your hand. It just kind of
Mm-hmm.
flows through. And the other thing is, I did not realize there were so many equivalencies in terms of transport. Like
Mm-hmm.
you've got what the pressure gradient, voltage gradient, velocity gradient. Well, I knew velocity gradient, excuse me. But you know what I'm
Well, there's a
saying? The
lot
fact that they
of
all
that.
share that same structure and that same form
Yeah,
is
absolutely.
nuts. I never realized that.
Yeah, absolutely. I mean, like, so in just like in a nutshell, the nice thing about thermodynamics, if you have an idea, just a simple idea, and that idea happens to be like violating any laws of thermodynamics, just right away, it's gonna be like telling you, no need to spend time, effort, and money on trying to do experimentations. So don't move to the next milestone, which is transport phenomena. Don't move to that.
Right.
And thermodynamics, this is the beauty of it. It's just like it's almost inequality. It's not going to be like telling you, here is your idea, here is how it should go. It's not going to dictate how that goes. It's going to either tell you what you're claiming is physically impossible or physically possible. Now, if it's physically impossible, you saved a lot of effort, you move on. If it tells you it's possible, now you move to the next milestone, which is a transport phenomena. And transport phenomena is nothing but telling you how far are you deviated from equilibrium.
Right.
So if you have, thermodynamics is all about chemical equilibrium, mechanical equilibrium, thermal equilibrium. If temperatures are the same, if pressures are the same, if like potential, the chemical potential is the same or Gibbs free energy is the same, it's an equilibrium. There is no flux. There is nothing. So there's no transport phenomenon there. It's just gonna be like telling you if you have a given state variable like a pressure or temperature, here is your end. Here is how it ends for you. Now in transport phenomena, that's like now if you are how far you are shifted from equilibrium. You introduced a mechanical deviation, you increase the pressure, you increase temperature, or you have increased the concentration of a given component on one
Yeah.
side of a
Right.
phase versus another phase. That's where transport phenomena jumps in, and it's basically the study of fluxes. It's like tells you how fast or how slow you can go from A to B that has been dictated by thermodynamics.
That is really cool. That's really cool.
And if we are talking about like majority of like transport phenomena tend to be like majorly vectors, like mass transfer, height transfer, or if you have electrical energy, any type of energy in general, or mass transfer, it's gonna end up being a vector field because at the end of the day, if we go back to just like basic physical definition of what a scalar quantity versus vector quantity versus like a tensor quantity, it's just a mathematical way of how I can define a property. Like if I would be like saying, if you would come and ask me, hey, how is the weather in Louisiana? So you'd be like saying, oh, the temperature today is like 86. You don't require anything beyond that. You don't need beyond. Once you're
That's
in,
true.
say,
Yeah.
60 F, that's it. That's completed.
Yeah.
What does it mean? I don't need to be like telling you 86F in direction of Louisiana or the direction of Alabama or in direction
Yeah,
of
I mean, you're
Texas.
right. You're
It
right.
doesn't mean anything. It has no value. Now you move to the next phase, which is like if you move from a scalar, which by the way, if scalar, vector, and tensors are pretty much like they are all tensors, but the difference is it's 0 degree is a scalar, first degree that's a vector, second degree that's the one that we are associated with in fluid mechanics, which is stress tensor. But like if you move to the vector side is nothing but like again it's an intuitive kind of thing. If someone be like telling you, did you know I was running after this dude? Normally, you would be providing two things, like the speed at which he left and the direction at which he left. Like if
Right.
I would be like telling you he ran 5 miles per hour, you are going to stop there and be like, in which direction? Because you're not going to be running 5 miles in all directions.
Oh, that's really cool. Yeah.
So it's pretty much that's why, like that's where this mathematical identity or mathematical definition came later on. Is because like it's coming from the core physical meaning of it. Then you go to the higher level, which is like people be like talk about, the second degree tensor. Second degree tensor, that's basically, as the name implies, you're gonna need to define a magnitude, and you are going to need to define a direction for an action and a direction for a reaction. Like in a very simple nutshell approach, if I am playing football and I will be like throwing that football coming off my hand can be going in the same direction as my arm. So my arm is the action force. The football itself is like can be taking the same direction as my hand. It can be taking the direction of my hand with a spin. It can be taking it can be like going exact opposite of the direction of my hand. I can be like my hand can be like going almost horizontally, and I just let go at the last minute, and it just like go in a whole different direction. So that's what the tensor is. The second degree tensor, you're gonna need to define a magnitude, and you're gonna need to define how the action, what was the vector field of the action, and what was the vector field of the reaction itself. And that's why, like in fluid mechanics, you can have like layers of viscous layers shearing or basically moving against one another, but the force is perpendicular to the direction of the flow, which is goes like against anything in vector field. Because in vector field, normally, if you have a force, the acceleration is going to have to be in the direction of the force. If you have like if you have a heat flux, it has to, you have a temperature difference, the heat flux, it has to be in that same direction between that heat flux. Only in momentum transfer, where you can actually have a force that's perpendicular to the direction of the action force in the first place. So
All
that's
right, now
where
I
the
understand why
second
fluid
degree
mechanics is so much worse. That sounds awful.
it's a little bit complicated, but pretty much it's pretty much like telling you, if like in vector, if I have a 3D in a vector field, I need three components. But because in a second degree tensor, I'm gonna need for every component, I'm gonna need a magnitude, and I'm gonna need two directions. I'm gonna end up having a matrix that's basically 9 by 9. You're gonna have to be like having almost like 9 components. Why? Because like every component is gonna have two directions. So it's gonna be xx, xy, xz, yx, yy, yz, etc. So pretty much that's where it's coming from. The mathematical complexity is one thing, but at the end of the day, it's this matrix that's going to completely define what you are looking for. But just this is pretty much the basic physical understanding of why fluid mechanics tend to be like a little bit complicated than heat transfer and mass transfer. Heat transfer and mass transfer, you have only one force, concentration gradients, and that concentration gradients, if it's inside the same phase, then it's purely concentration gradient. If it's a concentration gradient across multi-phase, which is liquid phase versus vapor phase, then where thermodynamics will jump in and basically have to account for the phase equilibrium, because it's not going to be like $1 for $1. Now you are comparing euros to dollars. So now that's where thermodynamics is going to be like starting to be jumping in and basically tells you concentration in liquid phase versus vapor phase. No, you don't look at those two the same. You have to find the equivalency there. The same applies for heat transfer. You have only one force, you have one ingredient there, which is the temperature deviation from equilibrium. If you have temperature difference, you have temperature deviation. Same applies for electrical fields. At the end of the day, it's going to be like potential difference. That's what make electrons flow. You have that's what the name coming from. It's a potential difference. There is an energy difference between this end and this end, and that's what leads to flow of current. So simply speaking, we get accustomed, whether it's in school or whether we go to career, we always like. Majority of the notions that gets brought up is first and second law of thermodynamics, and the
Right.
reason despite there's four of them. The reason why is pretty much zeroth law is pretty much like a basic kind of it's like we take it for granted, like breathing and oxygen. Like the zeroth law is all about temperature or thermal equilibrium, which is pretty much like telling you if an object A and object B have been in contact for a long time, very very long time, or have the same, or basically are in thermal equilibriums, you have the same temperature. Or if object A is in equilibrium with object C and object B is in equilibrium with object C, then object A and B are in thermal equilibrium. That's pretty much the whole idea of thermometer. The
Well,
thermometer
so sorry,
yeah.
if you don't mind, for those who are unaware, do you mind covering what the first three laws are, since they are really the meat?
The first three laws or first?
Yeah. If someone doesn't know.
So, Zeroth law is all about thermal equilibrium, just like telling you if like two bodies are in contact for a very long time, they have the same temperature. First law of thermodynamics is all about you're starting your initial amount of mass and energy that you started up with and move to the next state for a final state. You cannot end up with more than what you started with. So
Right.
It's a pure common sense. Like just like to take out the nuclear energy out of this equation just to make it a little bit simpler because of the equivalency of the mass. Pretty much it's like telling you if you started with 20 kilojoule, you cannot end up with 50 kilojoule. Or 50 kilocalories end up with more than 50 kilocalories. That's what the first law of thermodynamics is. It's all about the heat the heat you provide into a system. You should expect the same amount of heat out of that system, or same amount of energy out of the system. Which again, there's a big thing, a big mark there. Energy in and energy out has to be the same. You don't need that energy out does not need to be useful. It doesn't have to be useful for
That's
your
very well said. Correct. Yeah.
So that's pretty much that's the first law of thermodynamics. It's telling you energy in must be equal to energy out. Second law of thermodynamics is going to be like telling you energy in versus the energy out. The energy out, whatever useful energy that you want to get out of your system, is never going to be converting 100% of your energy in. And it's pretty much common sense. We feel it all the time around us. And the reason that's being said, if you look at the lowest form of energy, which is heat energy, what's heat or thermal energy in the first place? It's all kinetic energy. It's all molecules like bumping into each other randomly in all type of chaotic directions. It's all random motion. Now look at the far extreme side relative to the heat energy, which is electricity, which is the highest form of energy. It's pretty much about like an energy that has a direction. You have a power plant on one side, and you have a commercial.
Oh, I've never thought about it like that. That's cool.
Yeah, so that's like the highest form of energy because it's energy under control. You are giving it a direction. It's like almost like when you go take, like if you have like 5 dogs, for example, or you're walking dogs, and you have 5 of them. You know that it's going to require energy to harness them to go into one direction.
Yeah.
From your, they are not going to spontaneously all go in one direction. You're going to need to provide energy in order to make them move into one direction. So they are spending energy, but they are not spending energy while just like dragging you behind. They are spending energy because they are trying to go in a given direction, but you are spending energy trying to confine them to go in a specific direction. So that's pretty much the second law of thermodynamics. You have heat energy that's almost chaos, random, molecules going in random directions, and you're trying to make that energy have a focus, have a direction. And in doing so, you're gonna need to waste energy. You need to spend energy. And that's why you have a concept like entropy that's basically telling you you cannot extract 100% of the heat into useful work. However, The opposite is true. You can get electrical heater with 100% efficiency. Why? Because it's super easy to make everything chaotic. That's what entropy loves. That's spontaneity. If you have electricity and you want to make it go random, that's pretty much what the electric heater is. Yes, you can get 100% efficiency there. No, there is no issues. But in reality, it wasn't 100% efficiency because that electricity did not come out of vacuum. There was something that made that electricity in the first place. So the overall system entropy is still going down. Sorry, it's still increasing. Stop. So anyway, that's pretty much the second law of thermodynamics. Third law of thermodynamics is pretty much like when you are going into the quantum realm or when you are really getting super cold. And the third law of thermodynamics is trying to tell you you can achieve at 100% ideality, pretty much like you can get the entropy quantity into a zero value if you go to 0 Kelvin. If you go to absolute, the absolute value on the Kelvin or Rankine, and you can deduce kind of two things there. It's either thermodynamics is laughing at us as basically like telling us, yes, you can make the entropy to be zero, but you're never going to be able to get to 0 Kelvin. Or, in reality, if you get to 0 Kelvin, you can get basically the system to be completely ideal. However, in reality, we have never been able to get to the 0 Kelvin. We have been super close to the 0 Kelvin, but we never got to the 0 Kelvin. And if you think about it, from heat perspective, which is going to be the case, if you're gonna need to go to 0 Kelvin, whatever chiller that's providing that value for you has to be below that value.
Right.
But you cannot be at 0 Kelvin in the first place.
Right.
So that's and not to mention the other aspect of this, when you actually start to be getting entangled between classical physics and quantum physics, where superconductivity start to be floating around, and having something like helium flowing against gravity. So there's a lot of other forces start to be popping in that realm, and that's where higher type of theories and hypotheses like quantum gravity might be the solution in the future to be able to catch on this.
That is really deep. You want to talk about something simple like enthalpy?
So, enthalpy. That's the next slide, huh?
Yeah. See, I'm trying to give you some nice transitions there. I thought that was a good one.
Like that. So if we look pretty much at the first law of thermodynamics, it's pretty much if you started already working, just new, or had your first opportunity as a co-op or intern, you'd always get to be catching up here's your gross bonus or gross salary, and the first thing that comes to your mind, you already know that's not going to be the money that is going to end up in your pocket.
Yep.
So this is the first law of thermodynamics. First law of thermodynamics is the gross energy that you have, which means not all of that budget, all of that currency is going to be ending up for you to enjoy. Some of it is going to end up being wasted. All of us know it's going to end up being, some of that's going to be taxed. So that's pretty much the first law of thermodynamics is all about the energy gross salary. So energy is since the beginning of the whole Big Bang. Just let's move with that concept till someone comes along and basically, well, Big Bang was wrong. There is another concept for that. But just for now, assuming it's the Big Bang, the energy, the universe started was a one given and finite amount of energy. Or even the solar system started with a star has a specific amount of energy or mass. The sun has been spending all this mass, turning hydrogen into helium, turning into energy that basically comes to us. Life started on the planet. Plants came along, started making photosynthesis, turning carbon dioxide using the photosynthesis pretty much, which is electrochemical energy, turning carbon dioxide into carbohydrates, comes along the animals, comes along the human beings. Those animals along with the plants, back in time, millions and millions of years, turned out to be fossils. Human beings, millions of years later on, used those fossils to be using space rockets in order to be going to outer space. So you are seeing the energy transformation. The energy is almost the same. It's just transforming from one form into another as a whole. Whether some of it is going to be ending being wasted, not utilized by any being or being entity, versus
Right.
what's useful, that's a whole different aspect. But the total energy has been constant. It has been constant. Some of it end up being a waste that I cannot utilize. Some of it gonna end up being useful in one form or another. That's pretty much first law of
Sorry.
thermodynamics.
That is very well said, and I do want to reiterate something because it seems like it gets missed a lot, right? And you said it prior. You will never get access to 100% of the available energy. Something's always going to be lost, and typically when we talk about that loss is entropy, right? So when we look at these novel processes that are being proposed, right? They say take this energy, convert to that energy, do this and that, and then you're going to get this product at the very end. The thing that gets lost in that discussion is the equivalent of taxes, right? Entropy. Entropy gets its share at each stage of that process. It always gets its cut. And when you get to the end, there really isn't, compared to where you started, you really did not, your efficiency, the way I look at it, the amount of energy you converted to something useful at the end is very low.
Yep. So I mean, if we think about it overall again, like if we look at the fossil fuels, natural gas.
Right.
Natural gas is there. It wasn't created from magic. It just created by older, kind of like millions of years ago. The Earth itself as a planet worked and fossilized all these things that we explore. The natural gas can be drilled, and I can almost instantly I can break that chemical energy, and I basically extract all the energy from it to make a given product, whether it's a chemical product or it's going to be used as a source of energy. Anything else, like if it's electrical driven, intuitively speaking, you're going to have to be asking yourself where the electricity is coming from. Well, if the electricity is available, you can do a lot of things. I mean, if the electricity is there, you can do whatever because it's already energy source available. It's how to get the electrical energy, because electric energy is not like fossil fuels. You can just drill them out.
Right. It's not just readily available.
Exactly. So you're gonna have to go back and see where that starts. If it's starting from a solar cell or a wind farm, yes, that will be not 100% still renewable, because at the end of the day, those solar cells are using rare earth metals that requires a lot of energy to extract them and purify them. And the same applies for the wind farms, because at the end of the day, they are made of polymers, metals, and cement, and all these things. So they are relatively renewable, but at the end of the day, it's not 100%. Because again, you go, but if, like, for example, if the electricity coming from a natural gas or a coal-fired plant, then that's definitely not renewable in any sense at all, because it's one of the most inefficient ways, actually, of trying to utilize that energy. Because let's assume that you have been using that electricity to be heating your stove, like you're turning electricity into heat. Well, the natural gas was heat source that spent a lot of natural gas to get relatively, as we know from second law, relatively not 100%, it's going to be like, I don't know, 60-80% of that electricity. The rest is wasted. And then now I'm taking those 80% to turn them back into heat.
Right.
Now I compare this to what if, like, I just took the natural gas to get the same calorific value out of it. I would find that if I'm using an electrical source that's coming from fossil fuel for a heat appliance, I would be way more efficient actually using an open natural gas source than using electricity.
Right.
Because if I have a heat engine, it's always preferable to take the route. Basically, the second law of thermodynamics is literally telling you, if your application or basically get your application as lower as you can get in terms of energy form. Because the higher the energy form that you are going to get, the more taxation that you are going to have.
I like that. So do you want to go to the next slide and talk a
And
little
this
bit
is
more about
basically
entropy?
the recipe for the net gross salary, for the net salary, which is
Right.
basically like we already know intuitively. Everybody knows it intuitively, whether you're getting it in your check, whether it's you're going out there, the first thing that you're asking, you're buying an air conditioner or buying a heater, the first thing that you would be asking, not like how much energy or power is on that air conditioner. The first thing that comes to you is like you're asking the vendor. That's actually how you compare vendors. How efficient is your equipment?
Right.
Second law is very
Right.
intuitive. It's very deeply intuitive. It's just the concept of the entropy as a name. We just don't talk about entropy in the news like we talk about energy. So energy as a term we are just familiar with because throughout our whole life we actually get like at the news all over the place, energy, 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 and it's part of everyday life, like you're literally dealing with it, whether it's in your computer or in your stove. Entropy, on the other hand, we are connected to it, but not as strongly. We just intuitively deal with it and but like quantify as a quantity. It's called entropy. Entropy is nothing but like a representation of how efficient any appliance in your house is, or how anything that takes place in front of you looks intuitive or counterintuitive. Like if I just randomly played something in front of you, like an egg being unbroken or a glass getting unbroken, you would know that that's not doesn't make sense
No,
because
that
normally
yeah,
the other
yeah,
way around.
yeah.
And it's deeply engraved in us. It's actually the second law of we're actually way more connected to the second law of thermodynamics more than first law. It's just the way the second law we get, like basically it's the same idea when you are leaving school and going to career or working in a chemical plant. That's literally how it feels when you are already intuitively understand the efficiency and how stuff that's broken gets unbroken. You already know that's not true. That's literally how the entropy feels like versus that. So in that sense, the entropy is like arrow of times. You always call it the arrow of time because it's like the flow of time. Normally, entropy of anything increases in the same direction as time flows, and that's pretty much like everything is getting more disordered as the universe gets older. That's how everything looks like. Uh, in the beginning, there was a lot of abundance of high energy hydrogen, and as the universe ages, hydrogen is going to turn into more helium. Helium is going to turn into more carbon. Eventually, everything is going to be turning into iron, and you can't extract any more energy out of this because anything beyond iron is going to be like an endothermic kind of a process. It's going to require energy to turn into higher elements. So that's how the flow of time looks like. We are always going into a state of order, into complete state of chaos.
From my side, I really want to say thank you for your time. I really do hope you enjoyed and that you walked away with something new. Again, to reiterate, our goal is to create material that helps to educate young engineers, young minds, and to hopefully bridge the gap between academia and industry. If you enjoy this video or any other content we create, please let us know, leave a comment, or send an email to sciencemadesimple@outlook.com. We are always looking for new topics to cover, so if you have an idea, hit us up. As always, this was Scientifically Simple.